Welcome back. Today we're going to continue our exploration into the underlying principles of the Shellstars. Today we'll be talking about how we calculate the rate of closure from the crossing vector and the muzzle velocity. Just to warn you, there be math aheads. Okay, from our graphical example and video 10 and 24, we know that the three lines we are concerned about are the rate of closure line, the muzzle velocity line, and the crossing vector line. Also from video 10, we set our muzzle velocity to 7.26 inches per turn and our crossing vector at 6.35 inches per turn. So first we're going to simplify our triangle. We just want the four segments of the crossing vector, muzzle velocity, and rate of closure, so we have equal time on each of the vectors. Just going from this to this. Now we're going to rotate it. So we have our crossing vector, muzzle velocity, and rate of closure. And we're going to zoom in so we only look at a single segment. So we're going to zoom in right here. So anything we do on this triangle will apply to the full triangle because of the triangles are equivalent as long as you maintain the proper angles within. So, and we're going to zoom in and enhance. Well, enhance is kind of the wrong word because this is literally the same image, just zoomed in. So that's why we have these little artifacts here in the big dot up above. So here we have our crossing vector, our muzzle velocity, and our rate of closure segments. Now we're going to start calculating the rate of closure solely based on the CV and MV. So first thing we're going to do is drop a line down from the peak down to the base of the triangle, dividing into two parts. And so the length of the rate of closure segment should obviously be segment AB plus the segment BC. So now we just need to calculate the lengths of these two segments. And here is where our good friend trigonometry comes into play. If you think of the blue line as the x-axis and the purple line as the y-axis, the formula for the blue segment is x times the radius. In this case, the radius will either be the CV or the MV times the cosine of these inner angles. So actually draw those in. So AB is the crossing vector, or technically the magnitude of the crossing vector, times the cosine of E. And BC is the magnitude of the muzzle velocity times the cosine of F. Combining those two together, our rate of closure is this formula right here. Now, before going further, we need to talk about attack vector rounding. Attack vector does everything in multiples of 30 degrees. So your ship could be at angle 0, 30, 60, 90, 120, 150, and 180, and obviously this can wrap around to form the complete circle. This makes doing cosines extremely simple, because the cosine of 0 degrees is simply 1, cosine of 90 degrees is 0, cosine of 60 is 1/2 or 0.5, and the cosine of 30 degrees is a 8.66, like something, keeps going on, but we simply round that to 0.9 to make life easy for us. And obviously, once we get over the top of the triangle, keep going the other direction, we have the negative values as well, all the way till we get to 180 degrees the opposite direction, which would be -1. This is just simple trigonometry. You can find this in any trig book or various websites online in case you need more information about this. Now back to this. So we know our crossing vector and our muzzle velocity. So again, our crossing vector is 6.35 inches per turn. Our muzzle velocity is 7.26. So now we need to talk about the angles. First, we'll talk about the crossing vector angle over here, E. So if we look at the graphical example again, between the rate of closure and the crossing vector angle, so rate of closure line is this one right here. Crossing vector angle is right here. there's obviously one window difference, so that's 30 degrees. Next, we have to look at the muzzle velocity. So between the rate of closure and the muzzle velocity. So this is the muzzle velocity one right here. This is the rate of closure. As you can see, that is 2 windows, so that is 60 degrees. Popping all 4 numbers into our formula, our rate of closure is 6.35 times the cosine of 30 plus 2.25 or 7.25 times the cosine of 60. Simplifying that further, it's 90% of 6.35 plus half of 7 1/4. And just walking through the math, our final rate of closure for the entire turn, remember, these numbers are for the turn, is 9.345 inches per turn. If we divide that by 8 to get per segment, it's 1.19 inches per segment. If you remember from video 10, we measured our rate of closure at 1.14 inches per segment, but we were actually measuring the actual angles and the actual distances with a ruler. And here we're just using rounding, so we come extremely close with just the minor bit of rounding that we did. And in the game, it all kind of washes out anyway, so this minor bit of rounding, it's pretty trivial. It doesn't really impact the overall scheme. At worst, you'll be off by a segment for impact time. Now, mapping this back to the worksheets for Shellstars. This should hopefully start looking obvious. This is the rate of closure worksheet in the big section of worksheets for the Shellstars. And we're not going to really worry about remainders right now. Everything will be still done in inches. So again, this is our triangle right here. Just a reminder, so obviously this CV right here corresponds to this CV. This MV corresponds to this MV. And we want to get our rate of closure, which is down here. And again, our crossing vector is 6.35. Our muzzle velocity is 7.26. And our 2 angles are 30 and 60 degrees. Our formula, if you recall, for rate of closure is the segment AB plus BC. And so our rate of closure works out to this formula right here. And also I mentioned earlier that because we're just a single segment worth of lines for the triangle, but we can easily expand this out everything by 8 to get the full turn, and all the math still works out the same. That's why we can use the values for a turn and just divide by 8 to get a single segment. Okay, so these 2 columns, the CV column obviously corresponds to right here, so that's AB. The MV column corresponds to this segment over here, BC. So obviously, this part of the formula right here corresponds to this formula right here, and this formula over here corresponds to this part over here. So we start popping in the numbers. So crossing vector and muzzle velocity are pretty simple to put in. Now the adjustment, that's actually taking the cosine of this angle. So we have cosine 630 and cosine of 60. And when we simplify, it's 0.9 and 0.5 respectively. And as we do the math, we end up with 9.345 inches per turn. 5 by 8, 1.19. Same thing we had earlier in this video. So that's how this triangle right here maps to the worksheets. Now, how do we get these 2 numbers without spending a lot of time measuring stuff on the tabletop with a ruler and protractor? Well, that's the shot geometry table. As you can see here on the 2 sides, we have our muzzle velocity adjustment and our crossing vector adjustment. That corresponds to these 2 numbers right here. And if you're not familiar with converting percentiles into decimal numbers, 90% comes out to 0.9, 50% comes out to 0.5. Crossing vector interestingly enough, we can go negative because the ship can be flying away from you or towards you. If it's coming towards you, it's adding its velocity to the shot, so you have the positive adjustment. If it's flying away from you, your shot has to catch up to it, hence it has the negative adjustment. All these values right here correspond to these angles. So 0, no, cosine of 0 is 1, so that's 1. Cosine of 30 rounds to 0.9, still 90%. Cosine of 60 rounds to, actually doesn't round, it's exactly 50%. And cosine is 90 degrees is 0. That same thing for down here. And as we go over the top of the triangle, they'll start getting into the negative values. So how do we decide which one of these values to use? How do we determine the actual angle? That's decided by this inner part of the shot geometry table, which we will be doing in a later video because that's a lot more math and a lot of comparison and a lot of examples to show, so you understand what's going on. Now, one of the things we can do at this point is rename our angles E and F. Now that we have our shot geometry table up and showing, angle E is simply the angle from the course offset, or course offset angle, or simply course offset. This angle right down here corresponds to these values down here, which is the course offset. That means angle F is basically the aim shift angle, as it's based on the number of windows you have to shift your aim. So with that in mind, we can conclude that we only need to have 4 variables to calculate the rate of closure. The crossing vector, or more accurately, the crossing vector magnitude, the muzzle velocity, which is also a magnitude, the course offset angle, and the aim shift. If we know those 4 items, we can calculate the rate of closure, and therefore, once you calculate the rate of closure, we know the distance between the attacker and the target, we can determine how long it will take to actually impact. So tying this back to a graphical example, here we have our attacker in purple and our target in green. We know that somewhere along the line here, this is the course that the impactor will follow. How fast it'll go along this track, we don't know. What we do know is the muzzle velocity and the aim shift. Remember, the aim shift is the angle from this imaginary line right here and the muzzle velocity angle. We also know the crossing vector magnitude as well as the course offset. So we line everything up. We know that our rate of closure for the turn is this line right here. So then we divide by 8 and we get our rate of closure value, which is 1 segment's worth of movement. We just simply keep counting forward. This is what we do when we fill out the time track. So know that in 1, 2, 3, 4, 5 segments, we will reach our target and thus impact the target. So technically in the game, we count backwards from here. Those be, impact plus 1, plus 2, plus 3, plus 4, plus 5. Okay, the other way to look at this is we have our two triangles. We have our AB segment and our BC segment. If you recall from earlier, those add up to the rate of closure. We simply calculate it by taking the cosine of the course offset angle times the crossing vector magnitude to get AB, and then the cosine of the aim shift angle times the muzzle velocity magnitude to get the BC segment. Add those two together, we have our rate of closure. Well, that's all I have for you today. Hopefully this gives you a bit more insight into what's going on under the hood for the Shellstar calculations. And remember, you do not need to know how to do this in order to actually play the game. Just follow the worksheets. They'll come out exactly right all the time. If you happen to like this video, please give me a thumbs up. If you didn't like the video, well, thumbs down, still feedback. I always appreciate comments. And if you want to see more videos of this nature, please hit the subscribe button. If you want to get notifications every time the video goes live, just hit the little bell next to the subscribe button. Like I said, that's all for today. I'll catch you all later.